Encryption Consulting virtual conference. It is my pleasure to introduce this session, Building a Quantum Safe Environment by John Leiseboer. John is founding CTO at QuintessenceLabs, PTI LDT, and is responsible for the research, design, and development of key management, ComSec, and InfoSec products. He is a member of the OASIS KMIP and PKCS 11 technical committees and has contributed to the development of NIST, IETF, and IEEE standards, including SP 800-90B and C and IEEE 802.6. John has worked in the field of communication and information security over 35 years, designing and architecting commercial and military communications and information security hardware, software, and systems. Please welcome John.
Hi, my name's John Leiseboer. I'm CTO at QuintessenceLabs. At QLabs, we build quantum cyber products that are designed to integrate easily into IT systems to provide protective measures resistant to current classical and future quantum attacks. Building a post-quantum safe crypto environment includes evaluating current crypto environments and making recommendations for achieving a quantum safe posture. There are technologies and solutions that can help provide a quantum safe crypto environment. Quantum resistant crypto algorithms, quantum random number generators, quantum key distribution, and agile key management. During this session, I'll present and demonstrate how IT systems can be hardened against cyber attack by employing a quantum safe methodology to migrate to a quantum safe architecture. I'm not going to talk about why we need to worry about quantum computing's threat to cybersecurity. There are plenty of papers you can read and talks you can listen to elsewhere on that topic. I'm going to start with the assumption that quantum computing will pose very real and serious threats to cybersecurity, and that we need to invest time and effort now in determining how to mitigate these threats. Quantum computers do things differently to computers that we use today. They can perform some operations exponentially faster than current computers. And because of this, quantum computers have the potential to introduce new cyber threats that weaken or break cryptographic measures. The threats from quantum computers currently come in three areas. Shor's algorithm completely breaks public key algorithms such as RSA. Diffie-Hellman, and elliptic curve cryptography. These are used for key exchange and digital signatures in today's systems. Shor's algorithm completely breaks public key algorithms. Sorry, I already said that. Grover's algorithms weaken but do not break symmetric key encryption algorithms such as DES and AES. These are used for encryption. Simon's algorithm and superposition queries can break most MACs, or message authentication codes, and authenticated encryption and association dated modes of encryption, including algorithms such as HMAC-CBC and AES-GCM. These are used for message integrity and non-repudiation. In addition to traditional technical and non-technical measures that you should have in place today, such as application whitelisting, application and operating systems patching, blocking suspicious email and web content, scanning for viruses, controlling movable media, educating users, and other things. There are several technical measures that we can employ specifically to address quantum attacks. These technical measures need to be and are just as valid for systems susceptible to non-quantum attacks. Firstly, symmetric key encryption using large high-entropy keys is resistant to quantum attack. A 256-bit key generated from a high-entropy true random source with an algorithm such as AES is believed to be quantum safe. There are products that already support this today. Secondly, quantum-resistant algorithms. New public key cryptography algorithms based on mathematical problems considered difficult for classical and quantum computers are being developed and evaluated for standardization. We're starting to see some products using these algorithms today. We should see more after NIST and other organisations have completed evaluation and made recommendations for use. And thirdly, quantum key distribution, which makes use of quantum effects to securely share random numbers between nodes connected by an optical channel. QKD is immune to quantum attack. While the theory of QKD is sound, as with all crypto systems, it's important to ensure that the physical implementation is also secure. QKD products are maturing and coming to market now. And some organisations are developing secure communication services using QKD infrastructure. An important enabler for migration to a quantum safe architecture is crypto agility. That is, specifying crypto requirements based on attributes rather than specific algorithms and key lengths hard-coded into applications. For example, instead of coding an application to use RSA 2048 for key exchange and AES 256 for encryption, the application could specify a policy, such as a credit card protection policy, that is mapped to specific algorithms and key lengths. This is supported in some products today and is enabled by key management protocols like the OASIS Key Management Interoperability Protocol, or KMIP. Crypto systems built around quantum safe architectures will be hybrid. They will contain more than one quantum resistant technical measure. We will see combinations of high entropy symmetric key encryption, quantum resistant algorithms, and quantum key distribution being deployed in quantum safe crypto systems. To ease the transition to a quantum safe architecture, it's highly desirable to easily integrate and interoperate with IT products that are in common use. This can be achieved by maximizing the use of standards-based interfaces and protocols. This chart shows how a hybrid quantum safe architecture can be deployed today with a wide range of IT components, such as encrypting storage, encrypting databases, cloud services, web and application servers, certificate managers, secret managers, virtual machine and virtual storage encryption, etc. The objective is to provide quantum safe protective measures while minimizing the impact to end users. And this needs to be done by connecting through standard interfaces and protocols that are already implemented in deployed products. The intent here is to have existing products with existing processes that users are using now be able to continue using those systems through having these standard interface and protocols in place and using crypto agility, find that the user experience doesn't change. We want to be able to migrate the environment and continue to use systems in a safer way without having to change user experience or the way users do things. What I want to do next is I want to flip to a live demonstration. And in this demonstration, I'm going to show algorithm agility in use. Firstly, I'm going to show a key management system that has a policy in place that's effectively called a credit card encryption policy. And that policy will specify an AES 128-bit key, which would typically be used for encryption and decryption operations. The applications, it's a very crude application, it's very low level. What I'll do is with that application, I will create a key by specifying the credit card encryption policy. We'll then see what that key looks like by downloading it in the application, inspecting its attributes, and also going back to the key management platform and having a look at what the platform has generated. We'll then, as we know that this particular key is not quantum safe. 128-bit AES is very secure, but not secure against quantum computing attacks. We'll have to change the policy to generate a 256-bit key. And then we'll go through exactly the same process. We'll create a new key, just specifying policy, not talking about algorithms or key lengths, and we'll download the key, inspect the algorithms through the attributes, and we'll see that what we have done here is created a new key. So we'll try and flip to the screen that demonstrates that capability. Firstly, what I'm going to do is I'm just going to display some very low-level information here. What I want you to remember is when we actually look at attributes, we'll get numbers, we won't get descriptions. And we'll see, hopefully, a number 3 show up, which indicates that the algorithm in use is an AES key. So just remember 3 means AES, and we'll come back to that in just a minute. I'm next going to flip to the key management screen, and I'm going to go to the policy section here. We're going to go to a particular type policy called an object policy. And the first policy in my list here is called the Agile CCN Encryption Policy. And we can see from the definition that this is a policy that will create objects of type symmetric key. And those symmetric keys that are created will be suitable for use with the AES algorithm and will be 128 bits in length. Creating this policy creates an associated template, what we call a policy template. And then when we have an application that uses this template, so specifies this policy, what it should find is that it gets a symmetric 128-bit AES key. So we'll go back to the command line here, and I'm now going to create that key. So as I said, it's a very simple application here. It's actually built around some sample code, and we're creating a key. The important things to see from this line are that we're creating a key with a name called Agile CCN1. Okay, and we're going to create that key and activate it at the same time. So I'll execute that line of code now. We've got back what's called a unique identifier, which will identify the key. We'll have a look at that in a minute on the management console and confirm that that key was actually created and is recorded there. I'm also going to now download that key and get the attributes from that key. So here we go. We've downloaded the key. I've specified the key I want by name, and I've asked for the algorithm and length attributes to be returned. And we can see here that the key value was returned. It looks fairly short. I'm pretty certain that's 128 bits. We can see that the algorithm is algorithm number 3. And you go back to the list up here. Remember 3 was AES. And the length is reported as 128 bits. So if we go back now to the key management console, and if we look at the Managed Objects tab, we can find that key. So the identifier starts 4A44, and that matches the identifier here starting with 4A44. And if we look a bit closer at this key, we can see that the name is the Agile CCN1 key, which is what we specified on the command line. And we can see that the crypto attributes here specify AES 128 for encrypt and decrypt purposes, which is what the policy required us to do. So we've done that, and that's an application of agile cryptography where we're using an algorithm that is not secure against quantum attacks. So what I'm going to do now is I'm not going to change the application, but I'm going to change the policy for this key. So I'm going to delete that policy, and then I'm going to create a policy to replace it. And we'll use exactly the same policy name so that we get the same template, which we can specify in the application. Configure the policy now. We're going to use AES 256-bit, which is resistant to attack, and permitted uses encrypt and decrypt. And we'll leave the other fields blank. I'll create this policy now. And that's been created. So remember, what we've done here is we've just created a new policy. Effectively, we've updated the policy to change this length attribute from 128 to 256 bits. So if we go back to our example here, and what I'm going to do is now is I'm going to run exactly the same command as I did before. I'm going to create the key, use the same template, Only difference I'm going to make now is the name is going to be Agile CCN2 instead of 1. So this is so we can see a bit of a difference when we look at the key in the key manager, and we'll activate the key. We've created the key. This time it has a different unique identifier. Starts with 7C1F. We'll get the key now. So I've retrieved the key. You can see that the key value appears to be much longer. In fact, it's now twice as long as it was before. Still got algorithm type 3, AES, and now I can see the length is reported as 256. So remember, all we did here was change the name of the template, the policy template, and that created a key with new attributes that the application can look at, and then knowing these attributes, it can then perform operations using this new updated key. Going back to the key manager, if we refresh our managed objects page, we can see now the second key is present. If we look at the last column, Agile CCN2, Agile CCN1, the two keys. If we interrogate the key number 2, the first on this list, we can see that its cryptographic length is now 256 bits. So what we've demonstrated there is the ability for an application unmodified to, through crypto agility, through policy settings, retrieve keys that are updated over time. Now, there was more happening in that demonstration than just creating and getting a key. The symmetric keys under the covers had other things occurring during the creation. And what was going on there? The symmetric keys were generated using a true random number generator. In fact, it was a quantum random number generator. And it was producing very high entropy true random key material. The keys that we created were wrapped with an AES 256-bit key generated using the quantum random generator as well. And those wrapped keys were stored on the local key management server. So they were well protected by a quantum resistant key. They were then replicated to remote nodes in a key management cluster. The replicated keys were protected by the high entropy symmetric wrapping key. In addition, they were protected by hybrid TLS, so that's standard TLS, augmented to use quantum resistant public key cryptography. And additionally, there was a QKD, a quantum key distribution layer, providing keys for an IPsec layer to carry the TLS sessions across the encrypted links. Finally, communication between the client and the KMS was also protected by hybrid TLS. This is an extract from the key management server logs showing entries related to the integrated QRNG. You can see that there are quite a few technical details there, but the main point is what it's showing is that a very high entropy true random number generator was being used to create the key material. This slide is showing an extract from the key management server logs showing that both classic and quantum resistant and hybrid algorithms used together were used for the session encryption, key exchange, and digital signatures for the TLS connections to the server. So the previous slide plus this slide demonstrate that we've used high entropy symmetric keys and that we've used quantum resistant algorithms that are currently being evaluated by NIST. And then this third screen is showing us the replication link information in that cluster of key managers. And this screenshot shows the replication status and configuration between the key management nodes in the cluster. In addition to the replication payload being wrapped with AES encryption using high entropy keys and being carried across a hybrid quantum resistant link, QKD keys were used with the IPsec encryptors to provide a third layer of encryption. I'd like to thank you for sitting in on this presentation. I hope that I demonstrated that work is progressing on several fronts towards providing technical measures to augment existing security practices, to provide safe, safety in a post-quantum world. I'd be more than happy to answer questions now if there is time, or if you contact me by email, we can answer questions later. Thank you again for your time.